Hello, my name is Sergio Gomez. My FIU ID number is 2832878. This is EEL3110C. We are group number 5, and this is laboratory 1.
Hello, my name is Naya Sanchez Lucero, and my Panther ID is 6115497.
So for activity 1, we were supposed to set up a simple circuit according to the activity. We chose a voltage of 5 volts, which falls in line between the 2 and 6.2 volts, and a resistance value that is equivalent to 0.7 kilo ohms. As is seen in the schematic, C and E are not connected, which means that we have an open circuit. In terms of the voltages applied across multiple points, I will show that in a moment. One of the comments I'd like to make is that we are showing 13.5 nanovolts in one area, and as far as we're concerned, that is equivalent to a 0-volt reference. We did have to supply a ground because a multi-sim online does not actually include a ground. And we had to include reference voltages to measure across certain points. Now I will pull up the spreadsheet. This spreadsheet right here is for the different voltages required. So we have VAB, that is across the resistor, is going to be 0 volts because the circuit is not complete. VBC is for the direct connection after the resistor. That's also 0 volts. VCE is going to be equivalent to the battery voltage. In our case, since the resistor is not in that segment, it's not going to impact the voltage coming out of the battery. And then VDE is equivalent to VBC in the sense that it's a wire that doesn't have any connections going to complete the circuit. So that is also 0 volts. Now VAD is going to be equivalent to VCE, and that's going to be 5 volts because that is measuring directly across the battery. Interestingly enough, the resistor not being there also doesn't have an impact because that part of the wiring is not connected. And then lastly, our amperage across I1 is, according to the system here, is going to be in the neighborhood of 10 picoamps, but that's basically nothing. So we're going to write down 0 amps for our tabulations.
So for lab 1 activity 2, we set up a circuit with a voltage source of 5 volts, which meets the condition of the greater than 1.2 volts and less than equal to 7.3 volts. We have resistor 1 in parallel, and that loop is going to be a closed circuit. And resistor 2 is in series, and that circuit is open. So for resistor 1, we have a value of 6 kilo ohms. That meets the condition of it being greater than 3.3 kilo ohms. And resistor 2 is 15 kilo ohms, which meets the condition of it being greater than the double of resistor 1. So for VAB, we have a potential difference of 75 nanovolts, which is basically 0. And this is because of the open circuit. For VBC, we have a potential difference of 5 volts, and this is because we're measuring the voltage across the battery. For voltage CD, we have, and I have this here in the spreadsheet, VCD is 0 volts because of, again, the open circuit. There's no elements here, it's just wire. VDE is 0 volts because of the voltage drop across resistor 1. And the AD is 5 volts. It's because of the closed circuit. And then for the current I1 is measured as 833.33 microamperes, and this is because of the closed circuit. And even though it's a small number, it's actually just 0.83 milliamperes, so there is current there. Unlike current 2, where it's an open circuit, so it's measured at 5 picoamperes, which is basically 0.
For activity 3, we were supposed to set up an ohm meter and then measure and tabulate RAB for 3 separate conditions. Condition A, we have resistor 1 greater than resistor 2 in a series circuit the resistances are additive, so RAB in this case will be 3 kilo ohms. In segment B, we have resistor 1 being less than resistor 2. Again, since these are additive, it doesn't matter. The total RAB is going to be equal to 1 plus 2 kilo ohms, so 3 kilo ohms. Lastly, for case C, for activity 3, we have R1 equal to R2. So 2 kilo ohms plus 2 kilo ohms, because they are additive, will be 4 kilo ohms in this series circuit. This is presented here in activity 3. So case 1, 3K, case 2, 3K, case 3, 4K, A, B, C, 3, 3, 4.
For lab activity 4, we have a closed circuit with the resistors in series. So this is for condition B, where resistor 1 is less than resistor 2. Resistor 1 has a value of 6 kilo ohms, and resistor 2 has a value of 15 kilo ohms. Here, the values for current for I1 and I2 are the same, with 238.10 microamperes, and this is because the circuit is in series. For VAB, the potential difference is 5 volts. VAC is 1.4286 volts. VCB is 3.5714 volts. And if you add up VAC and VCB, you get 5 volts. And in the demonstration video, VAB was actually -5 volts. And that would account for Kirchhoff's voltage law. It's negative because the voltage is being consumed by resistors 1 and 2. So for the values of VAB over I, we got 21,000 ohms, which would just be 21 kilo ohms. So that's due to Ohm's law. So the VAB divided by current gives you the total resistance. So if you add up 6K ohms and 15K ohms, you get your 21K ohms. So this is the circuit for condition A, and the only difference between condition A and condition B would be that resistors 1 and 2 are swapped, and this would just change the values for VAC and VCB. So those values would also be swapped because the voltage drop across them would be different. So now for condition C, we have set resistors 1 and 2 to the same value of 6 kilo ohms. And this has affected the circuit by making the voltages of VAC and VCB are also the same. And here are the values that we input for activity 4. For condition C here, we can see that the total resistance is now 12 kilo ohms, which is just the sum of the individual resistors. And we also have an increase in amperage from 0.24 milliamperes to 0.416 milliamperes.
For activity 5, we had 3 separate cases where we were using a parallel circuit with 2 resistors, measuring the resistance of the total circuit. So it would be RAB. Now with a parallel circuit, the way it has is 1 over the resistance of the total circuit is equal to 1 over R1 plus 1 over R2. In our case, for A, we have R1 being greater than R2. With this combination, our total resistance value ends up being 667 ohms. For case B, we went ahead and set up R1 to be less than R2. So again, same system, just reverse location of the resistors, but it's going to have an equivalent value to case A because we chose the same sizes of resistors, 1 kilo ohm for R1 and 2 kilo ohms for R2, bringing our total resistor value to 667 ohms. For the last case of activity 5, that's case C, we set the resistance value for R1 and R2 equal to each other, so 1 kilo ohm. Due to the way they add up, it ends up being a total resistance value of 500 ohms. Because again, 1 over R total is equal to 1 over R1 plus 1 over R2. So 1 over 1 is 1, 1 plus 1 is 2. The inverse of that is a half, so 500 ohms. And this is again presented in activity 5 right here. So case A, R1 is greater than R2, 667 ohms. Case B, R1 is less than R2, 667 ohms. And then case C, R1 is equal to R2, 500 ohms. For activity 6, we have a parallel circuit with voltage present. For the circuit we decided to build, we went with a voltage of 5 volts. And with configuration A, R1 is greater than R2. So in our case, we set R1 to 2 kilo ohms and R2 to 1 kilo ohm. Regarding the components going on inside of there, we have a voltage, well, we have a total amperage of 7.5 milliamps. And then that is consists of I1 at 2.5 milliamps and I2 at 5 milliamps. In terms of all the voltages, with the exception to AF and AD, everything else is 5 volts, because in a parallel circuit, voltage stays the same. The only thing that doesn't stay the same is amperage. That gets divided across the components that utilize it. The reasons that AF and AD are at 0 volts is because there's no component going through there, so there's no voltage drop to occur. And now VAB over I is equivalent to, and it's right here, 0.667 kilo ohms, which represents the total combined resistance value of the R1 plus R2, which would be actually 1 over RT, or R total, is equal to 1 over R1 plus 1 over R2. So that represents our first case. For condition B, we went ahead and set R1 to be less than R2. So in this situation, we set R1 to 1 kilo ohm, R2 to 2 kilo ohms. And the only thing that occurred is that the amperage is inverted. So we have 5 milliamps across R1 and 2.5 milliamps across R2, which is equivalent, once you factor that the resistance is swapped, everything else stays the same. In the last case, we set R1 equal to R2. So in our case, we set them to 1 kilo ohm each. So what ended up happening in this case is that our total amperage goes up to 10 milliamps because we have less resistance when they're added together. And then all our voltages stay the same. The amperage across I1 and I2 are now the same because the resistance values are equivalent. Here's our spreadsheet showing this information. VAB equals divided by I is equal to 0.5 kilo ohms. Again, everything else stays the same. Just because we went ahead and set them equivalent, the only real difference is that the amperage going through them becomes the same, which sets the total amperage to be higher for the circuit. Thank you.